And Eddie's here. All right, everyone is here. Excellent. Okay, let's go ahead and get started. Good morning, everybody. You don't sound very happy to be here. Let's try one more time. At least pretend for 2 seconds, okay? Fake it till you make it. Good morning, everybody. That was a little better. Okay, at least I heard you this time. All right, we've got a fairly exciting chapter this week. And at the same time, it's also rather simple, which is good because you've got that PSAT thing going on middle of the week, and I didn't want to give too much for you. So this works out very well. We're dealing with surface area. Okay? And the great advantage of surface area is that really it's not new. Right? You already did area. We know how to find the area of rectangles and parallelograms and triangles and trapezoids, and all these other polygon shapes. And any three-dimensional object is made out of other two-dimensional objects. So to find the surface area, it's just multiple area problems all in one, right? It's just adding them all up. Now, if you read through the text, which you should have, right, in your notes, you've got some shortcut equations that you can kind of use that would help you out on these problems. Okay? So save you a little bit of time. But don't forget that the surface area is still just the sum of the area of all the faces. So when in doubt, you're going to be like, oh, well, that's just triangles and rectangles. I can do that, add up some triangles and rectangles. That's all it is. That's all you need to really worry about. Okay? It's not too bad. And so this section is not new, but now we get to look at some interesting shapes because there's a lot of cool, interesting stuff in the world made out of these three-dimensional guys. Such as we've got this classic problem with how best to arrange a whole bunch of cubes. Okay? And the cubes are a simplified version. Right? But this is actually done and studied, this type of problem, by people in all kinds of industries who need to pack things up in as neat an arrangement as possible. Okay? If you've ever wondered why aluminum cans are designed the way they are, okay? That's a fascinating bit of mathematics behind figuring out how much can I get away with, right? Because they want to use as little aluminum as possible, so they make the walls as thin as possible. But if you make them too thin, then the can just crushes, right? So how do you get away with just enough strength? And they add the extra ridges around the top and the bottom. Like, all of that carefully considered with ideas like this. How do I best maximize or minimize the surface area for a given arrangement? Right? Greenhouses. Right? I threw both of these on there for the level 1 problems this week because I want you to see the comparison. These are not exactly the same size of greenhouse. Right? The rectangular one is 96 feet long, 23 wide, and the semicircular one is 100 long and 24 wide. So they're close to the same dimensions, but you'll find out that the surface areas are very different. Okay? And I think that's an interesting problem to consider, because this is, again, a practical application. Why, when you head out west and you see these things out in the fields, well, not in the field, but next to people's houses, you'll see like people have these weird round greenhouses. Like, why do they do that? There is a method to their madness, and the mathematics backs it up. Right? So for us here today, I'd like to do a couple of examples. Give you an idea of some of the more Trixie challenges that pop up when you go from regular area to full-on surface area. Okay? When you're dealing with a three-dimensional shape, first you get a couple of new things. Right? Two-dimensional circles becomes three different things in 3 dimensions. We've got cylinders, cones, and spheres. And they all have a different way of calculating their surface area. So that one you need the shortcut formulas for. It's not just adding more circles together. And then we can do other things like this. What's going on here? This isn't just a sphere, this is a hemisphere. So they've cut it in half. Right? That's another thing they will try to trip you up with. They'll be like, oh, here's a lovely little cone, and everything is just fine except I've sliced it down the middle vertically. Why would you do that? I don't know. But they could. And then you got to figure out the surface area of half a cone plus this half a circle at the bottom, plus when you slice the cone in half and you pick it up and you turn it to face you, now you have a triangular face on the middle, right? That's now a new surface that has presented itself. Okay? So when considering these things, especially when dealing with halves, you have to ask, wait, do they want all the exposed surfaces or not? Do we count this top circle or not? Okay? That is a question you're going to have to ask on every problem. When I say find all the surface area, sometimes they'll set it up with, like with the cube problem. Okay, if you stack these cubes, then you try painting it. Okay? Which faces end up getting painted, which ones don't get paint on them? Maybe that's a good way to think about it. If I hold this out in the open and I just spray paint from all sides, what gets paint on it, what doesn't? That's the exposed surface area. Sometimes they'll have to specify the surface areas except not this one, right? Or find the surface area minus the circular base. This one doesn't say minus circular base. In fact, it says total surface area. So that's a good hint that yes, we need to include the circular base, except this is a hollowed out hemisphere, right? Does exactly what it sounds like. Okay? They've carved this pumpkin and they've scooped out all the insides. So whenever you see hollowed out, your brain should immediately alert you to, hey, I'm going to have to do one extra operation. And that operation is what? Normally to find surface area, I'm adding up all of these surface areas. But if they say hollowed out, I must now do what? I might have to subtract, right? But watch out for that. What am I taking away? What am I adding here? Because this is now a physical 3D object. It has thickness to it, right? This isn't our idealized mathematical hollow hemisphere, right? This is an actual bowl. So you could take this object and you could spray paint it from all sides, right? And you could paint all down here and around the top and down inside, right? In fact, I have a bowl, right? And I painted the thing. And I painted it all around the outside. And I painted it on the inside, totally different color. You can see that, oh, we got to count that, right? All of that is now surface, right? So in looking at this type of problem, I need to make a list here. I'm going to make a list. I want to stay organized. That's probably the biggest issue with surface area questions, is keeping track of the things you've already counted for. So if we break this down into smaller shapes, basic pieces, what do we have? What's the first piece you notice that we'll need to find the surface area of? The what? You said the hollowed out part? So the inside dome part, right? We've got the inside. That's totally correct. Inside. And that is spherical. It's half a sphere. Okay, it's sphere divided by 2. Hemisphere is just sphere divided by 2, right? But we'll use the sphere formula to find that. We also need what else? The ring up here at the top? Yep. We'll need that top ring. What formulas are we going to need for that? What shapes is that made out of? Technically circles. It looks like, because it's perspective, right? If you look at this head on, it's a circle. But if I tilt it, now you see technically an ellipse. Ovals had flat sides, right? It's truly an ellipse. So we've got circles there. And then we need the outside shell, right? Which is another sphere divided by 2. Right? All of those get added together, right? They are all included in our surfaces. Okay? Add, add, add. Do I need to do any subtracting? Not in the big picture here. Not from this major list. But how am I actually going to find the area of this top ring here? Is it just the area of one circle? No. If we imagine we turned this so it faced us properly. Okay? We only want this part, the donut. And that's where the subtraction comes in, right? We've got to now subtract one circle from the other to get that part. Any questions so far? Well, let's get to it then. Let's start with the inside sphere, or inside hemisphere. No, I don't want that. Oh, gosh. Don't do that. How do I find the surface area of a hemisphere? Well, since I'm not counting the bottom of the hemisphere, right, it is just half of a whole sphere, right? We slice it off, and we're not recounting that bottom section. We've saved that. We've already accounted for that. That's the top ring, is the flat side. So we just want the round bit. Literally half a sphere. So 1/2 times surface area of a sphere. Four pi r squared. Excellent. If you don't have that memorized, that's okay. You need that somewhere handy dandy in your notes, so you can look it up quickly and easily. Okay? As long as you can find it. You're set. Okay? So we've got, let's just real quick simplify here. Half of 4 becomes 2, so now it's just 2 pi r squared. Oh, that's nice. What's r? Oh, we've got to find the radius of our inside sphere. Here are the dimensions they give us. Are either of those the radius we're looking for? No. So how are we going to get it? What do they give us? What is this number? What is this 1.25 centimeters measuring? Height of the inside portion? Of the outside? Height of the whole thing. And the height of a hemisphere is also its what? It's going to be the radius, right? Wouldn't this be big R, radius of the large one? Yeah? We need little r. We want the radius of the small one on the inside. Okay, so it's not that. So it must come from this. What is this number indicating then? Diameter of the small one. We'll call that small d. So if that's little d, then how do we get little r? Divide by 2, right? Okay, so d, so then that means little r is that divided by 2, which is how much? .93? Yep. Excellent. We've confirmed that. Okay, so now we've got .93. So we'll say the surface area of the inside hemisphere portion is 2 pi times .93 squared. Now we have to decide, do we leave this as is for now, or do we go ahead and get a decimal approximation because of that pi there? You can get a decimal approximation if you want. Okay. Maybe you will want to know that number by itself. But I'm eventually going to be adding it to other numbers. I'm adding it to other numbers that also rely on circles and spheres for their formulas that I know will then involve pi's, right? So this will be an approximation plus an approximation plus an approximation, which means I'm prone to include errors. Okay? If I start rounding now, my answer is going to be off. So I'd rather save rounding for the end. If I'm lucky, I can rewrite all of this in terms of pi. Maybe I can factor out the pi. And it's be like, oh, the whole thing, it turns out to be 1.25 pi. Right? If I'm lucky. Does that make sense? That, like, we could possibly do that. Right? That's something that comes from experience that you'll notice as you do some of these. Like, wait a minute, I want to save myself a little bit of rounding error here and avoid that. So we'll leave it as is for now. There's our inside number. I mean, we could square the .93. Would you want to do at least that? Let's get this in terms of pi. So what is 0.93 squared and then times 2? One point what? 1.73 pi? Okay. So how about, do we just do the outside now? Since it's basically the same process, right? Same formula? Outside surface area, also half of a sphere, which I don't know why I'm going all the way there. We know it's just going to be this, right? 2 pi r squared. Don't rewrite stuff that you already figured out. So this case is going to be 2 pi, let's call this one big R. So big R we said was 1.25 squared. So in terms of pi, that was going to be how much? Everybody else has a calculator here. Ashley, can you confirm? 1.25 squared times 2. Yep, 3 point, well, say it again. 3.13 pi. Okay. Now we just need the ring. So that area is going to be a large circle minus the small circle. Right? Area of a circle, pi r squared. So I'm going to write it as pi big R squared minus pi little r squared. Right? Because that circle, both of those circles, right, are exactly matching up to the radii of our hemispheres, right? No need to introduce anything new. Okay? We only have 2 circles to deal with. Call them big R, little r, to distinguish. But good with that? Do you understand why I write it this way? Okay, now fill it in. In fact, we can already factor out a pi from that. Pi times big R squared minus little r squared. So it's going to be pi times 1.25 squared minus 0.93 squared. We know our r's, very convenient. And we'll get how much pi in total? What do you get, guys? 1.25 squared minus 0.93 squared. 0.7? Have somebody confirm? You got the same thing? Yeah? Round it to only one decimal? Okay, so 7-0. All right. So now we can add them all up. Let's go. Need a new color, green. Now just add the three together, yes? So our total area is going to be 1.73 pi plus 3.13 pi plus 0.7 pi. Aha! My prediction has come true. Everything is in terms of pi. So my final answer can just be a multiple of pi. So let's see, 1.73 plus 0.7 makes that 1. Let's see, we got 3.83 there plus 1.73. So 6, 15, carry the 1, 5.56 pi. And what are the units? Centimeters, I found the area, so they're actually centimeters squared. Let's see, how'd I do? Where's my final answer? 17.44. Ooh. Let's run it. So somebody try it out. Fill in, use your pi button. 5.56 pi is about how much? See how close we got. What'd you get? Oh, that's pretty good. I had 17.44. That's pretty close, right? So because we had rounded these ones before. Did it tell us how accurate to get? It didn't specify how accurate. So if the directions don't say, default to 2 decimal places for your final answer, which means really we should have gotten 1 more decimal place with these. Right? If this is not your final answer, go to round to 3 decimal places. Then when you add them all together, your final answer you can round to 2, and you'll be right. Maintain some extra accuracy ahead of time. That's pretty good. Right? Off by a 1,000th of a centimeter, guys. You can't find that on your ruler, right? So that's pretty good. Okay. Questions on that problem? All right, I had another one queued up. Do you want to go through the other example together, or do you want to just start on your problem set? Any thoughts? Raise your hand if you'd like to see the second example. Raise your hand if you just want to start the problem set. No votes either way. Come on, guys, pick one. Is it from the homework? No? Well, I mean, it's from the book section, but it's not one of your assigned questions. So no? You just want to start on the problem set? Okay, start on the problem set.